So I think what I'm going to do for the second half is the following. I promised you another example of a reduced form for dynamic settings. And so I'm going to do that. That's the multi-arm bandit. I won't actually put up the reduced form because I'll describe it in an abstract way, but actually writing it out in detail is a little bit of a pain, but I'll give you a reference to where you can find it. There are only sort of one property that you need about this reduced form is that it's a polymatroid. And so the exact functional form is qualitatively is not relevant. Then what I thought I would do is, since this is supposed to be a tutorial, I felt guilty about not including a proof that the greedy algorithm gives you an optimal solution to optimizing a polymatroid. So I will do that proof. And as a bonus, I will actually do an extension due to Jack Edmonds, optimizing a linear function over the intersection of two polymatroids. And on the grounds that, it might be useful in the future. But parenthetically, there is a use for it. If some of you have read the paper by Budish, Che, Kojima, and Mierendorf? Milgram, right. The intersection of two polymatroids actually appears there, but it's not mentioned. So I'll reveal the secret. Okay. So multi-arm bandits. So the multi-arm bandits, in some sense, has become a canonical setting for dynamic mechanism design. It is one of the environments where we have the nicest results for dynamic mechanisms. And in part, you can interpret what I'm going to do this morning is explain why that setting gives you the nicest result. Because at a high level, it's no different from Meyerson's optimal auction once you write things down in the reduced form. Okay? So what is the multi-arm bandit problem? You have a set of arms or projects. I'll use the word project and then eventually switch over to calling them agents. Okay? Now, each of these projects has associated with it a number of possible states it can be in, and every state has an associated reward. When you execute a project or pull an arm, then in the state that it is in, you get the reward from that state, and the state transitions. So when you pull the arm or you engage the project, then there is a Markov chain in the background by which the state of that project then switches to some other state. That transition matrix in the mechanism design setting is typically taken to be common knowledge. So both the agent and the principal know what it is. Okay? And okay, now, if you don't engage a project, then its state never changes. So the only time the state of an arm changes is if you pull the relevant, the only time the state of a project changes is if you engage the project. Okay, this is an important assumption. Without it, no analysis, no really elegant analysis is possible. Have people looked at the variation where the state of a project can change even when it is not engaged? The answer is yes. It's called the wandering bandit problem. Okay? And by this is a clue to tell you that almost every conceivable variation of the bandit problem that you can imagine has been considered by someone on this planet. And there are a variety of names that are given to them. Okay? But I want to look at the classic bandit setting, and that's the one that I just described. Okay? The second important assumption is that at most one project can be engaged in any time period. Okay? So the picture you should have in your mind is a collection of projects. You can go to any one project and draw a number from it. That's your reward. The reward depends on the state in which that project was. And then after you make that draw, the state of that project changes. The state of all the projects that you did not draw from remains unchanged. Okay? And then you keep going back, drawing numbers. Your reward is the discounted sum of the rewards that you received. Okay? And so there is a discount rate, and you just do the usual sum by the discount rate going all the way to infinity. Okay? Now, in a remarkable paper, I think from the 1960s, James Gittens came up with an elegant algorithm for finding the optimal policy for this problem. Now let's think about what a policy involves. A policy must specify for every history of what you've seen so far, which project you're going to engage next. And there might possibly be a mixed strategy policy, so that the policy might specify a distribution over the projects that you will engage next. Okay? When you think of it this way, it's remarkable at all that there is a nice solution to this, and it's called the Gittens index solution. For every arm, there is a number called the Gittens index. So, Gij is the index of arm I, so I should be consistent, project I, in state J. And this is the set of possible states of project I. Okay, there is this number. I haven't said where it comes from. Okay? And the optimal policy can now be described as follows. At any time period, compute the Gittens index of each of the projects before you. Select the project with the highest Gittens index. Okay, easy to describe. Now, what is this thing? The Gittens index is computed by considering the following thought experiment. Imagine that I gave you a choice between executing project I when it is state J, starting now, or doing nothing at all. So you have only two choices. You can walk away, stop, or you can engage project I. It's a much simpler version of the Bandit problem, right? There's only one project that's interesting, and the other project is exit. Right? What is Gij? That is that's your maximum expected reward for that subproblem. Now, what is the solution to this problem going to be? It's basically engage, 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 stop. So there'll be some threshold where you stop, and then you can work out your expected reward. That object is your Gittens index. Okay? Is it easy to work out a Gittens index? Actually, the answer is no. Okay? Only in simple cases. In general cases, the problem of computing a Gittens index itself can sometimes be NP hard. Okay? Yes?
So it's the value of that simplified problem when you start in state J?
It's the value of that simplified. So given that that the project before you is in state J, start the clock. What's your expected reward from following the optimal policy? That's the Gittens index. Okay? And you compute it, pick the project with the largest Gittens index. That's it. Okay?
The largest current Gittens.
The largest current Gittens from among, yes, that's right. The largest current Gittens index. Okay. Now, I will not give you a proof of the optimality of the Gittens index policy. Once again, there are probably as many proofs of the optimality of the Gittens index policy as there are leaves on trees, each trying to outdo the other in terms of length, much in the same way Arrow's impossibility theorem delivered a flood of results. And I think even Iran has a proof, right? No, wait, so on the blog post, so on the blog post, the proof that you put up? The Weber's proof, okay. And so Weber's proof is the current shortest proof?
No, it's
Cyclists. Okay, right. Okay. So as I said, no shortage of proofs. Okay. Not going to do that. Okay. So now let's go back. How would one describe a policy for the bandit problem? As a function of the history so far, a probability distribution over which project you're going to engage next. Right? Those would be the variables that you would use. Now it turns out that there's a reduced form representation which uses a different set of variables, and here is what those variables are. Xij, the expected discounted number of times you engage project I when it is in state J.
When you start in stage J.
No, when it is in state J. Okay? Now you can see easily that this presumably might be easier to work with than the actual allocation rule, which is a function of the entire history. But then we have the usual problem. If I give you a bunch of these, how do I know that there is an underlying policy that implements them? Okay, so there is a theorem of Bhattacharya, Surkas, and I'm afraid I forgot the third author, and then subsequent generalizations, of which the most extensive is Bertsimas and Nino Mores. And this appeared in Math of OR. And let me give you the date, if I have it. (1996). So the generalization is there are other stochastic scheduling problems which also have a nice reduced form, of which the multi-arm bandit is only a special case. Okay? So the reduced form is that these x's live in a contra polymatroid. Okay, now what's a contra polymatroid? So take a polymatroid but flip the inequalities, change submodularity to supermodularity. Now, how does living in a contra-polymatroid help? Well, if I optimize a linear function over a contra-polymatroid, it can be done via a greedy algorithm. What is the greedy algorithm? It's exactly the Gittens policy. In fact, there is an interpretation of the Gittens indices actually corresponding to the shadow prices in the dual to this thing. So you can read the details of that in Bertsimas Nino Mores. Okay? And so this paper is, as I said, is a generalization of the earlier ones. It is prompted by the following question: which stochastic scheduling problems can be solved by an index policy? What is an index policy? For every project, at any time, there is a real number that depends only on the properties of that project, and you always engage the project for which that number is largest. That's an index policy. And so the question they ask is, what stochastic scheduling systems have an index policy as an optimal solution? The Bandit problem is the most well-known example, but there are others. Okay. Now, how does this help us? Well, let's add in an objective function. And let me do that here. So Vi of j is the value of project I when it's in state j, the reward from engaging project I when it is in state j. And then what would your optimization problem be? So associated with the Bandit problem would be a particular contra-polymatroid, so you'd be maximizing this subject to the xij's being in the contra-polymatroid. You may say, what happened to the discount factor? The discount factor is folded into the definition of the xij's. Remember, expected discounted number of times we engage project I when it is in state j. Okay? Now, what do these sort of constraints look like? Well, by analogy, let me point you to the earlier examples. So in the static case, remember, for allocating a single object, what were the relevant constraints? They were of the form that the expected quantity of the good allocated to the agents whose types are in S cannot exceed the probability that there is at least one agent whose type is in S. Okay? So these are basically, it's a collection of what you might think of as necessary conditions that would have to be satisfied. In the dynamic version, what were the constraints? It was the expected allocation to the boxes before me, plus the expected allocation promised to me must be less than or equal to 1. So as sort of a high-level idea, these are sort of the laws of expectation that have to be satisfied by your xij's. You write down all of them, and then you hope to God that they're enough to characterize the set of implementable xij's. Okay. Now, once I have this, what can I do with this? Okay. So I'm now going to build in a mechanism design problem in the following way. Let's imagine that the Vij, each project represents an agent, so I is an agent. Vij is the reward that agent I enjoys if they happen to be in state J. And now the catch is, this will be private information of the agent. Okay? And I'm the planner. I'm going to ask agents to report to me what they say is their value, in other words, essentially what their state is. And then on the basis of their reports, I'm going to decide which project to engage and what transfers to levy. Okay? And I want to do that. Let's say I want to do that to maximize my expected revenue as the principal. Okay? I could have done efficiency. Okay? The reason I'm not going to do efficiency is because efficiency, you can read about it in Bergman and Valimaki, but let me very quickly tell you how efficiency works. This is the problem of finding the efficient allocation. Vickery tells me how to do efficiency. find the value of the efficient allocation with all projects, remove a project, find the value of the efficient allocation. The difference is the marginal product of that agent. Just promise that agent that marginal product. Okay? The only wrinkle is I'm doing this all up front, and you might object to that. And so the question is, once I know what reward I have to give you, how can I allocate the reward over time? Right? So that's an accounting exercise now to make sure that there's a way to distribute the rewards in each period so that they add up to the target. But with this setup, I know what the target is. Okay, so I want to look at revenue maximization because I think that potentially might be more interesting. Okay. So here's the setup now, more formally. Each agent I has a one-dimensional type, theta I. Drawn from a distribution F. Now, notice what I'm doing. The more natural thing would be to assume that each of these objects is private information, but that would give me a mechanism design problem with multidimensional types. I want to stay away from that for the moment. So I'm going to assume that there is an initial piece of private information the agent has, and that initial piece of private information is going to determine their value for consuming at each state. And I'm going to do a particular functional form only because it makes life easy. So their private information plus some number that is associated with the agent and the state. And for the time being, I'm going to assume that this is not private information. Okay? Those of you familiar with ESO centers and the line of work that proceeds from them will realize you can get away with that assumption. Okay? And so I won't worry about it for the moment. I'll just focus on this. Okay? So this is private information here. Okay. So the agent can lie about this, but they cannot lie about this. Okay, and now I need one more piece of notation. Okay, so over here I have, so what's my mechanism going to do? My mechanism, you're going to make a report about your private information. And then as a function of your report, I'm going to make a decision about the expected discounted number of times I will give you the object when you are in state J. Right? Now remember, you can't lie about this, so I can observe which state you're in. Okay? And now notice I'm adding this up over all the possible states. So what does this represent? This represents this capital X, big X, the expected discounted number of times you win the object. Okay. So that's the value to Mr. I when they're in state J and their private type is theta I, and I've written it this way. Okay, let's go down now. So just remember, you cannot lie about the second, which state you're in. You can lie about your private information. Right. Okay? Now, some algebra. Let's write down the Bayesian incentive compatibility constraints. So Pi of theta I is your expected payment for agent I when she reports theta I. Xi of theta I denote the total discounted number of times agent I receives the objects when she reports theta I. That's this object that I wrote down here. Okay. Here's incentive compatibility. Right? So this is your private information part, right? Because this is part of your reward. So you pick this up every time you get the object. And then there are the rewards that you accumulate along the way because of the state that you're in, less the payment that you must make. And that must be bigger than or equal to what you would get by misreporting. Now you can only misreport the theta portion. Okay? So that's the expected discounted number of times you win the auction, given that you say your private information is sigma I instead. This represents the expected number of times your project is selected when you're in various states, given that you said your private information is sigma I, less the payment you must make. Okay. Now, what I'd like you to notice that if it weren't for these objects here, the R's, this looks exactly like the incentive compatibility constraints for myosin. Agreed? Okay, let's do the usual thing. Let's interchange the roles of theta and sigma I. And this is what you get. So this is sigma I pretending to be theta I. As usual, let's add the two and hope many things cancel, and they do. And after you rearrange things, you get, aha, something familiar, which is that the expected number of times you win the object, expected discounted number of times you win the object should be increasing in your private type. Okay, so we're off to a good start here. Pretty much everything is textbook. Okay. You can use the same envelope argument to say that the payments are bounded above by this. Okay. And so now we can write down the problem of finding the revenue maximizing mechanism this way. Maximize expected sum of payments, subject to monotonicity on the big X's. No payment can exceed this. And that the expected number of discounted number of times you receive the object had better be equal to these Xij's, which are the reduced form representations, and then the Xij's had better live in this extended contrapolymatroid. Yes, Phil?
On the previous slide, is there a reason not to fold the sum over J into the P, just to find a new P?
You mean these ones? But notice this depends on the allocation rule, right?
Well, they define that to be...
Oh, yes. You could, I see what you mean. You could...
P hat I is sigma I, is that...
Yes, absolutely. You could do that as well.
Exactly like the Meyer.
Yes, you could do that as well. You could just, yes, that's exactly right. You can just treat this as the actual payment.
Yeah.
Right. Okay, so we're there. And now what do we do in myosin? Well, we use these inequalities to eliminate the x variables. I mean, to eliminate the p variables, right? Okay, and so then we substitute out the p variables, and you get this object. And then let's eliminate the capital X variables. And that's what you get. Now notice the little xij's, these are your decision variables. the expected discounted number of times I give the object to Mr. I when they're in state J, given that they reported that their private information was theta I. And what I'd like you to notice is I've got our familiar virtual values. So notice I've got the reward of the state, Rij, plus your virtual surplus, because the theta I is what you have private information about. Okay? And so now notice I'm maximizing a linear function of these x's, and these x's live in a contra-polymatroid. So therefore I know there's a greedy algorithm. And if I dig hard, what is the greedy algorithm going to look like? It's going to look like the Gittens index policy, where the Gittens indices are adjusted to account for the virtual values. Okay. Okay, now, of course, I've made life easy for myself by making the theta i's being the only private information. What happens if I want the report of the state to be private information as well? All right. So there are sort of two tricks to doing that. So I think in Pavan, Siegel, Toika, one way of accounting for that is by assuming that for any misreport of type or state, there is an equivalent misreport where you truthfully report the state, but you misreport the type. So in other words, any misreport that you can think of where you misreport theta and the state can be mimicked by one where you just misreport the theta, but not the state. All right? So if you're willing to buy that, then there's no loss of generality here. Okay? Okay. Now notice what this approach has done is all of the messiness and the difficulty associated with the bandit problem is all folded into this. I'm not even touching it. I know nothing about stochastic processes. Right? And once again, we get sort of the same lesson as we do from Myosin, that at the end of the day, it is not the allocation, the space of allocations that really matters. All that matters is take the incentive compatibility constraints into the objective function with Lagrange multipliers, give them a new name, virtual values, okay, and then hopefully the resulting optimization problem can be solved by a greedy algorithm, give it to the person with the highest virtual value. Okay? So the two examples I gave you of dynamic problems, the banded one, more complex than the first one involving the secretary problem, make me think that maybe there's a lot of mileage to be had from looking at the reduced form representations for dynamic mechanism design problems. I believe in shameless reverse engineering, meaning we know how to solve static problems, so we solve dynamic problems by turning them into static problems. How do I do that? Reduced form representations do it because they essentially turn a dynamic problem into a static problem. Okay. Now, one puzzle that I still have, and I don't have an answer for it, is I'm unaware of the use of reduced form representations in repeated games. One could ask a similar question there when I'm trying to characterize the space of achievable utility payoffs. Right? So I have a strategy, you have a strategy. We could think about the game in terms of our strategies. Those are complicated objects. But what if I just want to focus on what is a feasible payoff pair? In a sense, I'm asking about a reduced form representation. I know of no approaches to the study of repeated games which do it through a reduced form representation. And it's not even clear to me that that would be possible, and I wouldn't even understand what the obstacle would be to that. Okay. But I leave that as a question. Yes, Sarah?
So you said regarding this unknown Rij, there are two approaches. You mentioned one, like mimicking.
Mimicking, and so the other approach is in a paper by Kakade, Lobel, and Nazarzadeh, where they have an additional round of communication after, I think, the first pull. I don't remember the exact details, but the way they get incentive compatibility on both dimensions is to have an extra round of communication somewhere in the mechanism. Yes?
So it seems like the polymeter is very important, but how should we expect the problem to become the problem structure of this polymeter?
So not all economic problems will have the structure of polymatroids. So now let me just make an assertion. If they don't, you're not going to get anything interesting. So move on to something else. Right? Why do I make such a statement? Well, if you think, we build we're solving the mechanism design problem because we want some qualitative insight into the structure of the problem. The only way we will be able to intuit some structure is if the optimal solution to the mechanism design problem is easy. Now, what is easy? Easy are, in my mind, greedy or priority rules. And greedy and priority rules are intimately associated with polymatroids. There is no formal statement that I can give you, but there's a large body of work that somehow says the two are inextricably linked. And that's the justification for the assertion that I made. Right? Now, even in the cases, right, so you could say, but wait a minute, if we go back to myosin, if the virtual values are not monotone, then a greedy algorithm is not optimal, right? We know that. But what does myosin do? The ironing procedure essentially says, no problem. I'll take the original priorities, adjust them by the Lagrange multipliers in such a way that they will be monotone, and then again I can use greedy. Right? So I don't see any way to get around the need for polymatroids. Yes?
Another question is, I've seen some papers who use a different methodology to solve the problem, which is optimal transportation problem. What's the link between these two?
Okay. Okay. This is a transportation problem, and I call this the Hitchcock-Koopmans transportation problem. What makes this different from the optimal transport problems of Monge and Kantorovich is that I have a finite number of supply nodes, a finite number of demand nodes. Okay, so what does Monge-Kantorovich do? It turns this discrete problem into a continuum. So normalize the S's and the D's so that they add up to 1. Then I can think of this as a measure and a measure. And then what is this? This is a measure on pairs of measures, right? And then this is making sure that the measure on the cross product satisfies the marginals. And the question you asked there is, does there exist a measure on the cross product that satisfies the marginals to optimize some function? Okay? Now, the crucial difference is that for Hitchcock-Koopmans, which is the finite version, there always exists an optimal solution to the problem of optimizing a linear function subject to these constraints. For the Monge-Kantorovich, because you're working in infinite dimensions now, there need not be an optimal solution to the problem of optimizing a linear functional of the x's subject to these constraints. So that literature is devoted to identifying two things, actually three things. Two things. So one is conditions on the objective function or the space of measures to guarantee the existence of a solution, number one. Second, there are many possible solutions that you can imagine, and one of the solutions that they're interested in is called a Monge solution. So let's say these are the two measure spaces that I want to transport mass from one to the other. These are your variables. You're looking for a measure on the cross product. Okay? And sometimes you may want a measure on the cross product that satisfies a very particular property. There exists a Borel map from x to y such that mu of xy is positive if and only if y is equal to t of x. In other words, you can interpret the solution literally as taking a point in x and moving it to a point in the y space. Okay? And so not every solution to a Monge-Kantorovich problem will have one of these Monge solutions. And so a second line of work is identifying sufficient conditions on the objective function for such solutions to exist. All right. Is that okay?
How is it related to these polymatrix?
Okay, so the answer is so when we move to the continuum, the continuous analog of this is still true, where the summations are replaced by integrals, and then the n of t's are just, the n of t and t are still sets. So the results about the polymatroids all extend to the continuum case. It is still true that, so in other words, if you have the polymatroid property, it is still true that there exists an optimal solution to the problem of maximizing a linear function. It is still true that there is a greedy algorithm that finds the optimal solution. Okay? Yes? Ah, okay. That seems, wait, so the incentive compatibility constraint is imposed on the expected discounted, yes, so then, right, so this seems, yes, this seems to have the flavor of the reduced form in the Bandit problem. I did not know about that. So here we are. Did I write it down? Yes, this has the flavor of the Xij's, right? Yeah. And then do they have a reduced form, do they have a description of which Xij's are realizable as a profile of mixed strategies from the two players, right? So the question would be, I give you these Xij's, right? Xij for me, Yij for you, and then is there a profile of mixed strategies that realizes them? Right. Okay. So that's the question. So it's that sort of thing I've not seen. Okay. Any more questions about reduced forms and their usefulness or not, as the case may be? Okay, in that case, let me show you why the greedy algorithm gives you the optimal solution, and then also do the case of the intersection of two polymatroids. Okay. So I have a ground set of elements. I have a function that is non-decreasing and submodular. So this makes the function non-negative because it's non-decreasing. And I'm interested in solving the following problem. Let me remind you that all of you have actually solved this problem once in your life without knowing it. Let the ground set correspond to a set of vectors, let's say in dimension m. Let f of s denote the rank of that set of vectors. So you give me a subset S of vectors. F of S is the rank of that set. Now the rank function is, the rank of the empty set is 0. The rank function is non-decreasing. And wonders of wonders, it's submodular. Right? Do you buy that? So think, I have a set of vectors. Now I add a vector and I ask whether the rank of the set goes up. Notice the larger the set, the less likely it is that adding a new vector is going to increase the rank. Submodular. Okay. Now if the CJs are all 1, what have I written down? I have written down the problem of finding the largest linearly independent set of vectors. And we call that a basis. Right? Now how did you find a basis? Pick a vector. Pick another vector as long as it's not dependent on the other. Pick another one as long as it's not dependent on the other. It's essentially the greedy algorithm. Okay? But really the only property we're using is submodularity. There's nothing about vector spaces really that's crucial. Okay? And you'll see that in the proof. Okay? So what's the greedy algorithm? So first order the elements by decreasing weight. Let S superscript j be the subset consisting of the first j elements according to this order. Anything with a negative coefficient, obviously we shouldn't pick. So that's this. All right? Now, if you think of this as the rank function, notice what this says. The first object I pick, the first vector, well, that will clearly have a rank of 1. If it's not 0, right? Very good. So now let's look at this. Now let's look at the second vector in the list. Well, if the second vector in the list is in the span of the first, then the rank of the 2 is the same, in which case this is 0. Right? Okay. If the second vector I pick is not in the span of the first, then adding it increases the rank by 1. Okay? Okay, I've given you a solution. I haven't proved to you that it's even feasible. Right? So the first thing I have to do is prove feasibility. Right? Agreed? It's only the first k elements that receive any that can possibly be positive. Let me just write it out first, and then. sorry. My apologies. Oh, I'm sorry. No. So I claim this is less than or equal to this. Going from this to this is submodularity. Now over here, what do I have? I have a telescoping sequence. So all the intermediate terms cancel. This is monotonicity. Okay, so I've got feasibility. The next thing I have to do is prove optimality. So let's write down the dual. Okay. I will have one dual variable for each primal constraint. So let me call it y subscript s, because I have one constraint for every possible subset. Anything that is on the right-hand side of the primal goes into the objective function, into the objective function of the dual. The primal was max, so the dual must be min. Every primal variable corresponds to a column in the dual, in the primal, sorry. Every column in the primal becomes a row in the dual. Okay? So now, what is a column in the primal? Pick xj. What are we looking for? We're looking for all of the rows that contain xj. Translation. We're looking for all of the sets S that contain j as an element. That was max. Primal will be min, greater than or equal to. Whatever is in the objective coefficients in the primal will go into the right-hand sides of the dual. And as we had inequalities in the primal, in the dual, everything, all variables will be non-negative. So what I'm going to do now is construct a dual solution that satisfies that complements the primal solution, and that will be the proof of optimality. Okay? So here is the construction. Make sure I got that correct. And YSK. And then because there's no C, So I put down a solution. I have to convince you that it is feasible, well, it certainly satisfies the non-negativity restriction. I think it satisfies this. And how do I know that? Well, let's look at two cases. Supposing the index j appears here. So now you might be worried, why did I pick that index? You might be worried, but wait a minute. A set S that is not one of these sets 1, 1, 2, 1, 2, 3, 1, 2, 3, 4 is getting value 0. So maybe I don't satisfy this constraint. But notice I'm adding up over all sets that contain that. Okay. But remember, this thing is negative. So these are 0, clearly satisfied. Okay, next possibility is what if we pick an element somewhere here? Well, then we got a Cj that is strictly positive now. Okay? But there must be at least one of these sets 1, 2, 1, 2, 3, 1, 2, 3, 4, that covers J. And then notice the way I've constructed it. So 1 up to J is there, 1 up to J plus 1 is there, 1 up to J plus 2 is there. So I have a telescoping series, and these things will cancel, allowing me to satisfy this. Now, if you stare a little harder at this, you will notice the following. I've actually, when xj is positive, my choice of y's will actually have this holding at equality. Anyway, I have a feasible solution. Let's look at the objective function value of this solution. Right, that's the objective function value of the dual. I've simply taken these and plugged them into the objective function. But if you look at the objective function of the dual, that's precisely what the primal is doing. So here I've got difference of C's, here I've got difference of F's. Rearrange. That make sense? Okay. Now, what else does this give us? Okay. It says that every extreme point of the polymatroid can be described by solutions of this kind, priority rules. All right. Interestingly, we get another property, which is if the submodular function is integer valued, the solution is integer valued. So if your polymatroid is described by an integer submodular function, it says that every fractional solution that lives in the polymatroid is a convex combination of integer solutions. Okay, so now why is this kind of result relevant to that paper by Budish et al.? Well, they were interested in when fractional solutions that correspond to allocating indivisible objects can be implemented as lotteries. So polymatroid gives you one of these implementation results for free. As long as the submodular function is integer valued, you can interpret any fractional solution, because you might be interested in a fractional solution for equity reasons. Any fractional solution can be implemented as a lottery over integer. Okay. Okay. Okay, last result before I let you go, and we have until 12? 12:30, okay. So I have two non-decreasing submodular functions, and the interesting version of the theorem is when these are integer valued. Here I have one polymatroid, here I have another. I'm imposing both, therefore I'm looking at the intersection of two polymatroids. Okay. Each polymatroid by itself has integer extreme points. How do I know that? Take the greedy algorithm, maximize a linear function. I can choose the linear function so that the solution is unique. For linear programs, there's always an optimal solution at one of the extreme points. So, all extreme points are integral. All extreme points are integral. Okay. In the paper by Budish et al., this corresponds to one set of distributional constraints. This corresponds to another distributional constraint, set of distributional constraints. Okay. So these might be driven by supply and demand. These might be driven by capacity constraints that have to do with equity, for example. Okay. What's the result of Edmonds? So let me call this P subscript F, and let me call this P subscript G. Ed. Take a polyhedron, integral extreme points. Take another polyhedron, integral extreme points. Intersect them. Claim the extreme points of the intersection are integral as well. And Kim Sao is nodding his head, and you should be. This is an utterly unexpected result, because if you think about it, the surfaces of these polyhedrons could intersect in all sorts of ways and introduce new extreme points that weren't there before. Why on earth should we expect these extreme points to be integer valued? Okay. Unfortunately, the magic breaks down at 3. So, okay. So here is so these results come from combinatorial optimization. General rule of thumb: 2 legs good, 3 legs bad. So pretty much all of the nice results in combinatorial optimization break down when you go from 2 to 3. Right? And part of the so here is sort of an explanation. The matching problem, just find match boys to girls, is a special case of this, where this says no more than one boy is matched to any girl, no more than one girl is matched to any boy. Okay? If you do 3 polymatroids, you're doing tripartite matching. You're introducing complementarities. There is no way this result is true, otherwise we're all out of work. Right? In fact, intersection of 3 polymatroids contains the traveling salesman problem as a special case. So, which is why you're not, this is the most you can hope for. So it would, say again?
We have, a chain rather than there's more than 2, but it's pairwise, but there's an intermediary.
There's an then you can then you can break. You have to specify very carefully what the intermediary is and is not allowed to do. But if you're careful about that, then yes, then
I'm saying if you generalize this in that sort of way.
You can generalize it in that sort of way. And so there are some, there are some papers that do that. But the generalization, once you define carefully what the intermediary does, the generalizations are sort of fairly straightforward. Okay, so what we're going to do is we're going to look at maximize a linear function subject to x living in the intersection of the 2 polymatroids. And so now what we're going to do is I'm going to write down the dual to this problem. Let me write it down first and then talk about how we arrive at it. If you cover this up, this is the dual to the problem of optimizing over a single polymatroid. If you cover this up, this is the dual to the problem of maximizing over the other polymatroid. Right? So what is this? This is sort of what you'd expect if I have to optimize over this and this. Okay. So you give me an optimal dual solution. What do I want to pay attention to? I want to pay attention to the variables that are positive. So calligraphic F is the set of sets for which Y star S is positive. And calligraphic G is the set of sets for which Z star S is positive. Okay. So here's a new word. A family of sets is laminar if they look like this. Nested, or collection of disjoint nested sets. I claim that we can choose I claim that I can choose my optimal dual solution so that this set and this set are laminar. How do I know this? Fix the value of Z. Take it over to the right-hand side. What do I have? I have the dual to a polymatroid optimization problem. Now remember the dual solution that I constructed from the earlier argument. Y1 was positive, Y12 was positive, Y123 was positive, Y1234 was positive, and then 0, 0, 0, 0. So there was a dual solution that had the property that calligraphic F was laminar. Okay. Fix the Y, take it over to the other side. Repeat the argument for the Z. Okay. Okay? Now, the variables that are positive in the dual are going to give me binding constraints in the primal. Those binding constraints are the ones that are going to determine the solution. So let's just focus on the binding constraints. So what do the binding constraints look like? Well, remember by construction, this is laminar, this is laminar. So when I look at the binding constraints for this guy, it has to look something like this. Agreed? Right? Because if I take this over to, these are the sets. If you look at this, this essentially looks like an upper triangular system. And so therefore, how do you solve that? You start at the bottom, set it equal to the right-hand side. Right-hand side is integer valued. Subtract, well, you're subtracting it from an integer, so the next one is integer valued, all the way to the top. That's the proof. Okay? I skipped over one tiny detail, but I don't think, you can worry about it later, but that's sort of the essence of the argument. Yeah?
See where if you add another H function, you have 3.
Right, so that's exactly the wrinkle. So the wrinkle is I actually have two upper triangular systems, right? One that came from calligraphic F and one that came from calligraphic G. So this argument of doing the triangular system works provided they're just two. If they're three, the problem is that if they're three, the problem is that third one can cause interactions between the two systems. And that's what raises the difficulty. Okay. So this was essentially Edmonds's proof, modulo some tedious details. I mean, what he does formally is to show that the set of binding constraints forms a totally unimodular matrix. And totally unimodular matrices have the property that if A is totally unimodular, AX equal to B, provided B is integer valued, has all integer extreme points. Okay? And this is the heart of the result in Budish et al. When their implementation result. They're essentially exploiting the fact that the kinds of constraints that they have, I don't think they call them laminar, they call them hereditary. Right. So if you recall the paper, they have one result that says if it's a hereditary system, then fractional solutions can be expressed as a convex combination of integer solutions. If it's the intersection of two hereditary systems, hereditary is laminar. It can be expressed as a convex combination of two integer solutions, but three, all bets are off. Okay. Now, other than the Budish et al. Paper, has this result been used elsewhere? The answer is yes. It's been used in one other paper that I'm aware of, which is by Bikhchandani and Maimer about the existence of competitive equilibria in economies with indivisibilities. So the setup there is the following. Right, so let's see, how does it work? Okay, so let me write down the problem, the way they do it. I think it's something like this. So they look at an economy with two agents. No, hold on. Which way do I want to do it? I'm sorry. This is good J. This is the supply of good J. Two agents. This is agent J's utility from consuming a bundle S. Agent 1's this is agent 2's utility from consuming a bundle S. Your goal as the social planner is to allocate a collection of indivisible goods to the two agents so as to maximize total utility. What would an allocation be? It would be a decision about which subset of goods should go to which agent. And so the constraint would be, these are the subsets of goods containing element J that go to agent 1. This is the subset of goods that contain element J that go to agent 2. The total number of such subsets cannot exceed the available supply of good J. Okay, so if these, now notice I flipped it to less than or equal to instead of greater than or equal to, no problem. Supermodular, supermodular. So if the two agents have supermodular preferences, we know that there exists integer extreme points to this. The dual variables now correspond to these x's, which we can interpret as Valratian prices. And so the result is that in an economy with indivisible goods and two agents with supermodular preferences, there exist market clearing prices. Quasi-linear preferences, I should say. Okay? Okay. So that's all I had to tell you about, unless there are questions. Yes?
So, just look at this system equation corresponding to PF and G.
Right.
Suppose I don't know what is F or what is G. And I just manipulate some of those systems to F, some of them to G to make sure again I can cook up some modular F tilde and some modular G tilde.
Wait, so what I'm puzzled by is what does it mean not to know? So typically the F and the G come from the resource constraints under which you're operating. Right. So that they would, so that typically we would know them. In fact, as a general assumption, we assume in mechanism design that the set of resources, the set of feasible resources is common knowledge. Now, the moment you start to tinker with that, and this goes back to classical results of Hurwicz, so think of a Valratian exchange economy. Utilities are private information, but endowments are private information as well. Well, now the space of feasible allocations is the private information of the agents. Right? And then if you look at those old results of Hurwicz, almost nothing can be done in those cases.
My question is, suppose you have F and G, suppose F and G, one of them is not supermodular.
Oh, one of them is not. No, then
I can change some of the constraint S from F to G and define F tilde and G tilde and possibly recover some modular.
okay, so you're saying take a function and perturb it so that it is submodular or supermodular.
Let's just switch some of the S from F to G and from G to F. Because the system, look at the equation, just switch S as an equation for F and also corresponding.
Okay, so I don't think that kind of thing will work. What you might think about doing is you might say, I have a function F. It is not submodular, for example, but I could ask for what is the largest submodular function that approximates it from below, or the smallest submodular function that approximates it from above. All right? And then you might hope, look, if the approximation is good, then if I optimize with respect to the approximation, maybe I get a solution that is good relative to the exact F. Okay. So Paul Milgram actually has proposed something along these lines in the context of the spectrum auctions. And so Sven de Vries and I have a paper looking at this proposal of Paul Milgram's. And let me summarize it this way. It's a fantastic idea, but the claim that Paul makes in his book is not correct. And this idea only works, as far as we can tell, in very, very special cases. Now, this is just a statement about the particular way that Milgram proposed constructing these upper and lower approximations. That doesn't mean that there might not be cleverer ways to construct these upper and lower approximations.
Do those methods work in spectrum auctions?
So if you read Paul's book, let's see, Auctions, is it Markets with Complex Constraints? Right, okay. So the problem that he's set himself in one of the chapters of the book is to understand the following. We have an optimization problem which you can write down. So for the spectrum auction, you can write down the optimization problem this way. This is integer valued, but this thing is not submodular. Okay? What Paul observes is that the greedy algorithm, nevertheless, it's monotone but not submodular. The greedy algorithm, nevertheless, appears to produce solutions that are close to optimal. Right? So so this is the thing that Paul would like to explain. Now, Paul's conjecture is that while these functions f are not submodular, perhaps they are close to being submodular. And so then he defines a notion of what it means to be close to submodular. And then he says, okay, let's replace this with that approximation from below. And now solve this, okay? And now the hope you would have is, if this intuition is correct, the solution of this thing should be close to the solution of the problem with the, okay? That part is not correct. So in other words, if you look carefully, if one looks carefully at the paper, that step has not been done yet. Okay? So the mistake, so therefore if there is a mistake, in one of two ways. One, that Paul's intuition about the correct way to measure approximation is off. Okay? Or maybe it's simply, in other words, maybe even tiny departures from submodularity are enough to kill lots of structure. I don't know the answer to the question.
Okay, great.
Thanks.